In grade 8 level, in your school work anyways, basically we're talking about functions, right? Functions, and there's like a lot of these guys, okay? There's a lot. There's hundreds of them, but you've seen this one, right? Y equals x, which is a linear line, yeah? Y equals mx plus b, slope, m is the slope, and b is the y-intercept. So this is a pretty basic function. It's just straight line, goes up and down, yeah? Goes up and down. If the slope is positive, it goes up. If the slope is negative, it goes down. And then we saw a couple of weeks ago, we can have the next level, y equals x squared, okay? So if it's positive, if the a value, if it's a positive x squared, it goes up. If it's a negative x squared, it goes down, yeah? So these are both, if you notice a pattern, that's x, this is x squared. These are called polynomial functions. Basically, it's always going to be x to the power something. The next one would be x cubed, which we won't do just yet, but it looks something like this. It looks like an S, okay? And then you have x4, which is very, very similar to x squared. It's the same thing, but it's a little bit fatter around the base. These are the four main ones. And then from this, everything else is basically the same. x5 is going to be the same thing as x3, but it's just going to be fatter. And x6 is going to be this. Okay, all these are polynomial functions, okay?
Okay.
And so far, we've only done polynomial functions. Now let's look at a different type of a function, which is called an exponential function. Now, what in the world is this? So this is a function that goes that grows very fast. So it looks something like this, okay? An equation would be y equals 2 to the power of x. Now notice the difference. In quadratics, the parabolas, we did x squared, yeah? Which looks like this, x squared. Now notice how the exponent and the base, they flipped. Now the x went up to the exponent and then the 2 came down, right? So if there's an unknown in the exponent, right? Unknown in the exponent x, then that's called an exponential function, okay? Exponential. And why are these important? They're important because a lot of things in life follows an exponential model. Something like population growth, anything that grows or decays, right? Population growth, you can say like house prices, stuff like this, rent, yada, yada. Maybe even the cost of chocolates, everything. A lot of these things, they follow an exponential model. And how is it different from quadratics? The main thing about these guys is that they grow very fast, okay? They grow very fast. Now, what does that mean? Let's make a table of values. You'll see that this one is going to win, and when it wins, it's going to win big. Let's make an x and a y, okay? X and a y for this, x and a y for this. Now look at this. When x is here, let's do this first. When x is 0, what's the y value?
0.
0, yeah, x is 0, y is 0, and then you can 1, 1, yada, yada, right? 5 would be 25, yeah? And then 10 would be 100, and we can keep growing this very quickly. 20 would be 400, yeah? Let me do 999, and this one I can't do in my head, unfortunately. 999 squared, and that is 998,001, okay? So this one also grows, but the other one will grow way faster. Now, for this one, for the exponential function, what is 2 to the power of 0? What do you think? What is 2 to the power of 0 equals to?
Isn't it just 2?
No, it's not. 2 to the power of 1 would be 2, okay? 2 to the power of 0, and this is something new, right? Anything to the power of 0 is a 1. Anything to the power of 0 is a 1. So you can have negative 2 to the power of 0, that's a 1. You can have x to the power of 0, that's a 1. You can have x squared, y cubed, z to the power of 4, everything to the power of 0, that's a 1. See that? Anything to the power of 0 is 1. So when x is 0, y is 1. And when x is 5, this is 32. When x is 10, I think 2 to the power of 10 is 512. No, it's 120, 1024. 20, 2 to the power 20. Now look at this, look at the difference here. 20 here was 400, yeah? 20 here
Mm-hmm.
is like a million. It's bigger than a million, okay? Now 999, I don't even know if this is able to do it. 2 to the power 999. Nope, too big for the calculator to even give an answer. Okay? It just kind of
Mm-hmm.
jumped very, very fast, right? This one just went up 4 times. This one went up like 30 times. And from here to here, it's like way even bigger. So this grows very, very fast, okay? 999 calculators can't even give it. It's that big. Cool. So that's called an exponential function. And I'm gonna do a lot more with these guys. That was just a quick start, okay? So there's 2 types of exponential functions. It's basically the u and upside down u. This one, as it goes up, as it grows, this is called an exponential growth, okay? Exponential growth. On the other hand, you have, if it goes down, you can think of this as having a negative slope or an upside down u. This one is called an exponential decay, all right? What could be an example of exponential decay? Here, let me give you one. The temperature of your coffee. Okay, this could be one example. So this is time. On the x-axis, we have time, yeah? On the y-axis, we have the temperature. And as the time goes forward, the temperature drops. Another example would be maybe the price of a car or a phone or something. As they get older, they're worth less and less, yeah? So both of these are examples of decay. Can you think of one more thing?
Um,
So basically, what does that mean? As x goes up, y goes down. Doesn't it have to do with money? Oh, like this one. Here's another one. The amount you sleep on the x versus grades on the y. Right? The more you sleep or game or whatever, Netflix, any of these, the more you do these guys, the lesser your grade, okay? Exponential decay. Does that kind of make sense?
mm-hmm.
You with me so far? All right. Here, let's look at this one. Is this decay or growth?
DK.
It's decay, right? It's going down. It's going straight down. On the y-axis, we have temperature. On the x-axis, we have time of a cup of cocoa. All right, let's look at this. Let's ignore part A. Look at B. What is the temperature at the start of the experiment?
85 degrees.
Yeah, that's good, right? So they're basically asking you, initially it just means, or start means the time is 0. So they're basically asking you for the y-intercept, which in this case is 85 degrees Celsius, right?
Mm-hmm.
Part C, what is the temperature of the classroom? And for that one, you kind of have to think. It is given from the graph. The temperature of the drink will not get colder than the temperature of the classroom, yeah?
Mm-hmm.
Like it would make no sense if it's a hot drink, it's not even a cold drink. It's a hot drink. Let's say the temperature of the class is 25. There is no way this drink cools down lesser than 25, yeah?
Uh-huh.
So that kind of brings us to another property of exponential functions. They have an invisible barrier that they can never cross. In this case, it is at 20 degrees, okay?
Mm-hmm.
And this barrier is called it's a line, it's a horizontal line, right? Horizontal, and the term for the barrier is, mathematical term is called an asymptote. So this graph will never cross this dotted invisible line, okay? And which is also the answer to part C. The temperature of the classroom is 20 degrees Celsius. Cool?
Okay.
The coffee will never get less than 20 degrees, and that's an asymptote. So enough with the graph. Let's try doing some. I think we have done these guys before. So this is just basic number manipulation. Right, notice all these guys have negative exponents. Now 5 to the power 3 is not negative 15. Okay, that'll be 5 times negative 3. What do we do when there's a negative exponent? If you remember, I think we have done this. I don't know when, but whenever the exponent is negative, okay, what you want to do is you want to throw it in the denominator. Okay, what do I mean by that? Look at this. 5 to the power negative 3 becomes 1 over 5 to the power 3. Cool? Like, for example, if you have, I don't know, we did the exponent laws, right? Here, let me just recap this for you. If you have x to the power of a times x to the power of b, okay, if they're being multiplied, you add the exponents. What do you do when you're dividing? What do you do with the exponents?
You subtract.
You subtract, good, right? And then you can have this one as well, x to the power of a to the power of k. What do you do in this case? You just multiply the exponents together. For example, 2 to the 3 times 4 would be 2 to the power of 12. Okay? And then here's the last one. If you have a negative exponent like x to the power negative k, what you can do is you can toss it in the denominator and the exponent becomes a positive.
Okay.
So that's why 5 to the power negative 3 became 1 over 5 to the power 3. And you can plug 5 to the power 3 on your calculator and that becomes 125. Cool?
Yep.
What is negative 4 to the power negative 2? What do we do here?
You put it in the denominator again?
Yeah, you put it in the denominator. So the bracket is going to go with it, okay? Like that. What's negative 5 to the power of, negative 4 to the power negative 2? So what does that mean, right? Negative 4 to the power of 2 just means negative 4 times negative 4. That's a positive 16, okay?
Okay.
Negative 4 to the power of negative 2 is positive 16. Now look at C. Well, when we throw it in the denominator, what do we get? And this one's a little bit tricky, okay? Because the minus sign is not with the 3. You can think of this as negative 1 times 3 to the negative 4, okay? A common mistake would be people throw the negative sign with it down there, yeah? That's not right. The negative is going to stay on top, okay? And then you get negative 1 over 3 to the power of 4. Because this negative sign, the exponent does not apply to the negative sign. Look at the difference between B and C. In B, the negative 2 also applies to the negative sign inside because there's a bracket around it, okay? But in C, there's no bracket. That means the exponent does not apply to the negative sign. That's why it looks like this. And 3 to the power of 4 is 81. And the answer should be negative 1 over 81. Really, there's no difference though. Negative 1 over 81 is the exact same thing as 1 over negative 81. Doesn't matter what that negative sign is. You can also pull it out of the fraction. Just don't apply the exponent sign to the negative, because you'd get negative to the power of 4 and then you'd get a positive answer, which would not be correct. Okay.
Okay.
How do we do this one? Now there's a fraction with a negative exponent. How do you think we approach this?
Um.
This is what you do, okay? We're gonna toss it in the denominator like we did before, doesn't matter, okay? And the exponent becomes a positive, right?
Uh-huh.
And what is 2 over 3 to the power of 3? This one you can do it individually, okay? What do I mean by that? You can do 2 to the power, because the 3 applies, the exponent applies to both the numerator and the denominator. So 2 to the power of 3 would be an 8, and 3 to the power of 3 would be a 27. Okay,
Mm-hmm.
good so far? So when we have a triple level, okay, we don't want triple levels or 4 levels. By levels, I mean 1, 2, 3. We only want 2. We want a numerator and a denominator, okay? Now tell me, does a 24 go all the way to the top, or does it go here? What do you think? It doesn't have to be that complicated, right? Let me give you a hint. It's 1 divided by 8 over 27, yeah? That means we can flip this into 1 times 27 over 8. The 27 ends up going all the way to the top, and that's the final answer. Do you see that?
Mm-hmm.
Here, 4 over 5 to the power of negative 2. How do we do this? Step 1, throw it in the denominator, make it positive, the exponent, okay? If the exponent is positive to start off with, you can just write 16 over 25 in one step, because 4 squared is 16, 5 squared is 25. But because the exponent was not positive, we first have to throw it in the denominator, which would make it positive, all right? What's 4 over 5 squared?
16 over 25.
Correcto. Okay, now the last question, does a 25 go to the second level or does it go to the top level?
The top.
Yes, it goes all the way to the top. You get 25 over 16, and that's the final answer. Okay. Here's another question for you. 1 over 2 to the power of 3. Again, a triple level. Okay, we have 3 different levels. Tell me, does a 3 go to the second level or does it go to the top level?
The top.
All right, so I tricked you there. No, it does not. The difference, look at the difference between this and this. This one is 1 over 2 divided by 3, yeah? The other one, like we did before, is 1 divided by 2 over 3. Now, if you flip this, this goes all the way to the top, okay? But this one, no, it does not go all the way. It's going to come down to the second level. Look at this. Do you see the difference?
Mm-hmm.
So you have to be careful of the brackets, all right? Just because there's 3 levels doesn't mean it's always going to go to the top. It depends on where the brackets are, or which level has another fraction on it. Cool?
Uh-huh.
But if there's a fourth level, it can go to 10th level, but the 4 level, 3 and 4 is the most common. If it's a 4 level, the 4 always goes to the top, and 3 always goes to the second level. Here, let me show you. This is the same thing as 1 over 2 divided by 3 over 4. And when we flip the second fraction here, the 4 goes all the way to the top and the 3 goes to the second level, okay?
Mm-hmm.
So there's 3 possibilities, I guess. You can either have A over B over C, the c will go all the way to the top in this one. Or you can have a over b to the power, over c, and here it's gonna go to the second level. Or you can have finally a over b to the power c over d, and in this, d goes all the way to the top and c goes to the second. Okay, 3 possibilities. You don't have to memorize this, right? Just you can always do a divided by b over c to see where goes what goes what. Okay.
Okay.
You don't have to memorize this, but just remember to do this, and it's going to be different depending on where the bracket is. Okay, how do we do this one? You're going to have to use the exponent laws. Ideas.
For the first one, do you just subtract the exponents?
Yes, you just subtract it, or you add it, right? So you just get a 3. What about the bottom?
You multiply the 2.
Correct. So that becomes 3 to the negative 6. Now what? The answer should be a positive exponent. This is what you do, okay? Because we want a positive exponent, we're going to have to toss this upstairs, okay?
Mm-hmm.
And when you take it up and down, basically the trick is the sign flips. So you get 3 to the power 3 times 3 to the power positive 6 now, okay? The sign, it flipped. Cool?
Mm-hmm.
So what's that? 3 to the power 3 times 3 to the power 6. You add them, right? Because they're being multiplied, you add the exponents. There we go. And you're done.
That's it?
That's it, yeah. Easy as that. It's just addition, subtraction. That's basically what it is, okay? Just looks hard,
Okay.
but it's really not that hard. Let's try doing some of these, just so we're clear on what we're doing. And all these are, almost all of them are gonna be a one-step answer, okay? It says write with a positive exponent. What do we do for a? We're trying to write this with a positive exponent.
You put it in the denominator?
Yes, and you're done. Okay, you can plug this in a calculator if you want, but you don't have to do this part because eventually the numbers get so big that the calculators won't give you an answer. Look at B. What do we do here? Again, you toss it, right? You can just introduce a numerator and throw everything else in the denominator to make it a positive like that. Okay.
Mm-hmm.
Now, if you want to actually evaluate this, look at this. -1 cubed is just -1. Okay. 10 cubed is 1,000. Yeah.
Uh-huh.
So you're doing 1 divided by -1 from here and then 1,000 from here. That's the same thing as 1 times 1,000 over -1. So the answer is -1,000. Okay. If you want to evaluate it. Cool.
Mm-hmm.
Look at C. What do we do? So you can make it positive by taking it somewhere else.
You put it on the top?
Yeah, you put it on the top and you're done. One step. You can evaluate that if you want, but you don't have to. That's a 16 on a calculator. Yeah, just 2 power 4. Eventually you'll memorize this by the time you end up doing this in class, you'll have memorized some of these guys. Like I knew instantly 5, 4 was 1625. This is a very common one. And any to the power of anything is pretty common as well. But you don't have to memorize it. Eventually you will end up, that's just how it is. Let's look at D. We want a positive exponent. Very similar to B. Look at what we did in B.
Do you just put all of it over one? I mean under?
Yes, you can do that, but you have to be a little bit careful. The exponent does not apply to the negative sign, right? Look at the difference between B and D. In B, the exponent also applied to the negative sign, but in D, it does not apply to the negative sign. So what we're going to do is we're going to leave the negative sign in the numerator as it is, and we're going to throw the other guys to the denominator like that.
Okay.
Okay, question for you. Does 5 go to the second level or the top level?
The second level?
No, it goes all the way to the top because this is what we're doing. 1, -1 divided by 6 over 5 cubed, yeah? So it's the
Mm-hmm.
same thing as like this. So it goes all the way to the top, okay?
Oh, okay.
And you can just leave it as that because we don't have to evaluate. What about E?
You just put it under one?
Yeah. Now the question is, does 11 go, because we don't want the triple, right? We only want 2 levels. Does it go to the top or to the second level? You can always do this every single time by hand until you're comfortable with it. It's gonna go to the top.
Okay.
Look at F. So both of them have, so we gotta swap both of them. We gotta throw one up and toss the other one down.
So you just flip them?
Yeah, you should literally just flip them. So 8 to the power -1 comes up, becomes 8 to the power +1. Okay. And
Mm-hmm.
if that's what you meant by flipping them, but that's it. And that's the final answer.
Okay.
Did that make sense?
Mm-hmm.
It's just gotta be, yeah, it's just plus and minus, honestly, and then some multiplication involved, but it's very simple. Don't worry, we will do the harder ones. The harder ones will be it's very fun. Well, maybe not, but who knows? Let's do these guys. So for these ones, these are the exponent laws, okay? If they're being multiplied, you add the exponents. If they're being divided, you subtract the exponents. Look at A, and all of these are, I think, one-step answers. What to do in A? Do we add 8 and -8, or what do we do? What will be the answer?
You add them?
Right, so you get -10 to the power of 0, right? Because 8 plus -8 is a big fat 0. Now, if you remember, what's -10 to the power of 0? It is certainly not -10.
One?
Yeah, you remembered. Anything to the power of 0 is a 1. Doesn't matter if it's a variable like x squared z cubed to the power of 0. This is a 1. Everything to the power of 0 is a 1. Okay?
Okay.
Here, let's drift away for a second. Using that logic, what is 0 to the power of 0? And the answer to this question makes no sense. What do you think it is?
Is it still going to be 1?
It's still gonna be 1. How does that make sense, right? You have nothing and you're doing it to the power of nothing. How in the world is that 1? I can show you this actually. So let's bring another type of a function. Okay, like exponential function, it's gonna be I have y equals x to the power of x. Okay, cool. And
Mm-hmm.
for this, we are gonna look when x is 0, what's the y value, right? Let's check this out. When x is 0, what's the y value? And that's gonna tell us the answer. So our function is going to be, again, this is just a graphing calculator, very, very useful. Y equals, okay, x to the power of x. Yeah, look at that. That's what it looks like. Okay. Now check this out. When the x value is 0, right? When the x value is 0, it's basically becomes 0 to the power of 0. Do you agree?
Mm-hmm.
When the x value is 0, it just becomes, our function becomes 0 to the power of 0. Now what's the y value? Look at that. How weird is that? So 0 to the power of 0 is a 1. Okay. This is, math is weird, I guess. Math is weird. Cool.
But why?
Yeah, but why? So that's the whole thing. It's technically it's not 0, but if you have a calculator on you, right? If you have a calculator on you, just type in something. It's not, it's, I mean, this is still debated. Like 0 to the power of 0, and this is very stupid as well. That's how math becomes sometimes. Is that the answer is actually technically the answer doesn't exist. It's called indeterminate. We don't know what it is, okay? We don't know what it is. But math is a very big field. People have shown that it's 0, but people have also been able to show that it's a 1, okay? And depending on which one helps your cause, you can use either one of them. But technically, the answer is indeterminate. It does not exist.
Mm-hmm.
Like, for example, what's 1 over 0? What is this? What do you think 1 over 0 is? If you plug it in a calculator, it's going to give you an error. So calculators won't help you. 1 over 0 also does not exist, okay? It does not exist. There's no answer to this. But we say it's infinity, and that's the symbol for infinity. Okay? When there's a 0 in the bottom, the answer is infinity. 0 over 1 would be a 0. That's a fact. This is an easy fact. So anything, you can't really divide 0 by anything. You'll always get 0. So for example, 1 times 0 is a 0. 2 times 0 is a 0. That's where this comes from. But when you're dividing by a 0, like for example, 0, 2, the quotient is infinity, okay?
Mm-hmm.
Math can get really weird really fast, especially when it comes to zeros. Zeros, yeah, zeros is a culprit, basically. Zero is a culprit behind a lot of things. So basically the point is anything to the power of 0 is a 1, okay?
Mm-hmm.
Since we're talking about this anyways, what is the square root of 4?
2.
What is the square root of negative 4? If you plug it in a calculator, it's gonna give you an error, right? But what do you think it's the answer is? Because a lot of what we were talking about, calculators won't help us. Square root of negative 4. A common answer is negative 2.
But that's going to give you a positive.
Yeah, exactly. So that's not the answer at all. So that's a very common wrong answer. Okay, absolutely wrong answer. So the same thing. The square root of negative 4, it does not exist. Okay, it does not exist. But I'm telling you that it does, and that's now. Well, how does it exist? What is it? To see this, you have to get out of what we call the real number system. Okay? Real number system is this number line. There's a 0 here. On the left end, we have negative infinity. On the positive end, we have positive infinity. And every number is here, okay? Pi is here, or pi is 3.14, so it should be somewhere here. And then you have negative 10, you have negative quadrillion, whatever. This is a real number system, yeah?
Mm-hmm.
To answer this question, real number system does not help us. We're gonna jump into a different type of a number system, which is called, again, we won't do this, but I'm just gonna tell you just because it's kind of interesting. We're gonna jump into a different number system called the complex numbers, okay? And this is a field of math that we made up not that long ago, in fact. Well, long in terms of how long we've been around, but like a couple hundred years ago maximum, I think 100 or 200 years. Before that, this didn't exist, okay? But pi and things, we have known this for thousands of years, okay? Pi and like the sin x, you know, that function we did, the trig functions, we've known these guys for thousands of years. But
Mm-hmm.
this is a relatively new field when we're talking about the history of human civilization. Now, what's so special about the complex number system? In complex numbers, we have a constant called I, okay? I, just like pi, it's a constant, and I is equals to the square root of -1, okay? I is the square root of -1, it's a constant. Now look at this, -√4, I'm gonna rewrite this as root of -4 times root of -1. Can I do this? Yes, I can, yeah? This is mathematically correct, even using the real number system. But now we know the square root of 4 is a 2, and that is I, and there we go, that's the answer. Okay? The square root of -4 is 2i, where I is a constant from the complex number system. Let me see if Google can help us. Boom, there you go. Square root of -4 is 2i. See that?
Mm-hmm.
Kind of interesting, right? And you don't have to worry about any of this junk anytime soon, but it does exist. Okay? This
Uh-huh.
you'll probably see a lot of if you take a math-focused course or program in university down the line. And there's a very beautiful relationship that, well, beautiful, I guess that's relative, but there is a relationship that brings us from the real number system into complex. I know this answer is purely from the complex number system, but we could technically convert it into a real number system. And that gets even more complicated and weird, and that's for another time, but yeah. So that does exist, okay? So basically the
Okay.
point is math is weird, but it's interestingly weird. Maybe you can come up with some things of your own, you know, like there are problems in history that have been around for like hundreds of years, okay? That have been around for hundreds of years. And we've only recently been able to solve them. Only recently. I don't know if I've talked to you about this. There's some problems in math. They're called the questions. They're called the millennial problems, okay? You solve any of these, you get $1 million. If you're able to solve them. There's 7 of them, I think, or 8. So far, only 1 of them has been solved. But this question has been around for a long time. Why is it only solved now? Because the tools used to solve this problem did not exist up until recently. You know how the complex number, we just kind of made it up recently? There's other things that we kind of made it up recently as well. And the logic checks out. Math is basically logic based, right? The logic is good, but we've only recently invented a couple of different fields of maths. And only using those new things, we were able to solve that one problem, right? So these problems, the millennial problems, they will maybe, I mean, They will probably be solved, but not for a while because the tools needed to solve those problems don't exist yet, right?
Mhm.
Eventually they will be solved. Maybe not in our lifetimes, but eventually they will be solved. And that's maths, I guess. It's a pretty interesting field. All right, let's go back to these guys. Let's come back down to reality, I guess. 6 to the negative 7 times 6 to the 5. What does that give?
Um,
They're being,
negative
yeah,
6 out of negative 2.
what does that equal to? We don't want negative exponents ever, okay? I mean, technically that's still right, but we don't want negative exponents. How do we make it positive, the exponent?
You put it under 1.
Yeah, you put on a 1 and boom, you're done, okay? Do not say 6 to the power negative 2 is negative 36. Again, this is a very common mistake, and that is absolutely wrong. It's 1 over 36. Cool. I see people making this mistakes even like in higher levels, and that is wrong. Okay, that's a very common mistake. It's 1 over 36, not negative 36. And if you know anything about exponential functions, you will see that it never crosses the x-axis. Basically, it never goes into the negative y values. The y values will never be negative. Look at this function. There's a strict boundary on the x-axis. There's a wall that it will never cross. So there is no way some number to the power of this would be a negative number. Okay? At least not a positive number. Anything positive, doesn't matter how big the negative exponent is, it will never be a negative solution because it does not cross the x-axis. It never goes into the negative y values. But you don't have to like think of it that way, but that's why the answer is not negative 36. Look at C. What do we do here? Again, the exponent, this one is negative, right?
Mm-hmm.
We just toss it up. We get this. Yeah,
Oh,
well,
okay.
that's it, right? It's very simple. There we go. Same thing for D. This one is negative. What do we do?
You flip them again?
Yeah, you bring that one down, yeah? Don't touch the 11 to the 5 because that's all. You don't flip both of them, just this guy. We're gonna bring that down. It becomes this, right? And then you add
Mm-hmm.
them now. And don't worry about what that is. It's gonna be some big number. We don't care about that. So we don't care about what the actual number is. We just want it in terms of something to the power of something. Look at E. What does that equal
You
to?
put it under 1.
Yeah, good. You put it under 1 and you get this, okay? Do not say this is positive 9 to the 4. Again, a very common mistake and absolutely wrong. It's 1 over that thing, okay? It's 1 over that thing. F. Again, doesn't matter how many there are, you just multiply all the exponents. When there's multiple exponents like that, you just multiply all of them. So this will be 7 to the power positive 6 from the first two, yeah? And then what? What's the next step? This is the rule, right? So if you have a to the power of b to the power of k, it just becomes a b times k. It doesn't matter how many there are, you can just keep multiplying them, right? So what is this to the power of that? 7 to the 6 to the power of negative 2. And that's the rule.
7 to the power of
Yeah,
negative 12.
yeah, boom, easy. And then you toss it down, one and done.
Okay.
Okay, it's just plus and minus, honestly. It's just the rules that are a little bit, confusing, but eventually it won't be. And I'm gonna make sure of that. Haha. All right, let's do these guys. We'll just do a couple of complicated ones. Okay, look at E. What do we do? Focus one bracket at a time.
You could flip that one, the
Yeah.
second one.
We could also flip 8 to the -1, right? Like that.
Mm-hmm.
And then this one will completely flip. You get 4 and then 2, 3, right? They
Uh-huh.
want, let me just see what they want. All right. So then, look at this. 4 goes into itself once, 4 goes into 8 twice. So you have 1/2 times 1/2 to the 3. What does that give? So this is the same thing as 1 times 1. It's just a 1 in the numerator, and in the denominator we have 2 to the power of 1 times 2 to the power of 3. Okay, numerator is 1. What do we get in the denominator?
2 to the power of 4.
Yeah, and you're done. Okay, if you want to evaluate it, that's 16, but you don't have to do the last bit. Cool.
Mm-hmm.
F is also very similar. Look at this. We have a 3 here. We have a -2 here. We have the same base for these guys. We're going to throw this up, and what does it become? We're going to throw this up. And this one I brought it down. So what do we get in the numerator here?
Is the -2 going to be a positive?
Yeah, it is. It is going to be a positive. So you get -5 to the 3 times, again, when you toss them up or down, when you change their levels, the exponents, the sign, it flips, okay?
Mm-hmm.
The sign of the exponent flips. So when you toss this guy up, -2 becomes a +2. And then you have -5 to the power of what in the numerator? We had a 3 here, and we're multiplying this by -5 to the 2. The question is, what's the new exponent? We just want one exponent.
5.
5, and you are done, you see?
Mm-hmm.
And that's the final answer. No, nothing complicated. I guess that's if you know what is going on. But it's not that hard. The math is very simple, but it's just the tricks. The tricks are difficult. In terms of the math, actual arithmetic is just plus and minus for most of them anyways. All right, now this one. So we know the square root of 4 is a 2, right?
Mm-hmm.
You know something interesting about it? It's actually, technically, it's not 2. It's plus and -2, because -2 times -2 is also a 4.
Mm-hmm.
So technically, mathematically correct way of writing, whenever you get a square root, the answer is always going to be plus and minus, okay?
Uh-huh.
Because if you don't include the minus, you're missing half of the solutions. Maybe it does not apply to grade 8, but I guess you can impress your teacher. 7 is okay, 7 is good, but technically, as you go into higher levels, into bigger classes, it's plus and minus. It would be the technically correct solution. But why am I bringing this up? Look at this. When you have a square root, okay, that's the same thing as having an exponent of 1/2. Because square root means there's an invisible second root outside. Look at this one. Maybe there's a cube root, right? Cube root. That's the same thing as 27 to the power of 1/3. This guy, the root goes in the denominator in the exponent. Do you see that? Here, I can try another one. 4th power of 5 squared. What is that? It's 5 to the power of something.
1/4.
It would have been 1/4, but this one came with 2, so it's going to be 2/4. Okay? It was 1/4 because these have to the power of 1. Let's do this. 49 to the negative 1/2. We don't want negative exponents, right? Step 1, we're going to toss it in the denominator like that. Okay? And what does that mean? 49 to the power of 1/2. That means it's the square root of 49. And we know that's a 7, right? Boom, there we go.
Okay.
If you want to be technically correct, it's going to be plus minus, but don't worry about this yet. -8 to the power of 1/3. Tell me. And this notation is called a radical notation. You see, radical notation. So if we were to write this in radical notation, what does that become? Can you remember this is the root, right? This is the root, the denominator. It's the cube root of -8. And you can plug this in a calculator. That's going to be -2. What about C? In terms of the radical notation, what does that become? This one is the root, right? This one is the root. So look at this, very simple. 4th root of 10,000. And then the answer is this 10 on a calculator. Do you see that? Here. 27 to the negative 1/3. How do we do this?
You put it under a 1 to get rid
Yeah,
of the negative?
that's correct. And then what? I'm going to turn this is right now in an exponential notation. We're going to turn it into a radical notation. Okay. 1 stays 1 at the top. What happens in the bottom? By radical, I mean you got to introduce a 2nd root, 3rd root, 4th root or something.
The cube root for this
Yeah,
one?
exactly. The cube root of 27. And that is a 3. And boom, you're done. 1/3 is the final answer.
Okay.
Make sense?
All
Right, we'll pick it up next time.
right, bye.
Bye-bye.